Hello everyone, and in this lecture we're going to talk about different quality metrics that are used to assess performance of classification and regression models. We're going to talk about different ways how to ensure systematic quality assessment, and also we're going to introduce new kind of models, namely decision trees and ensembles like random forest, that can be used again to classify your data. Okay, in this episode we're going to talk about different quality metrics that can be used to assess quality of regression or classification models. So we're going to start with regression quality metrics, and just a reminder of the problem that we're going to solve in this regression context. So we have data representing a set of features and corresponding labels. Features are denoted by X and features by Y, and blue dots are different points in our data set. And we're looking for some kind of model that approximates this dependency. In simplest example, it could be a linear regression, linear combination of input features. The solution looks like a line drawn on this picture in red color, and predicted values y hat are denoted by red circles. So intuitive measurement of quality of your model is the distance between red and blue dots. One can measure this distance using, for example, root mean squared error. So when you have a mean squared error under the square, root square, so it may be better than regular MSE because it doesn't take into account outliers too seriously. The same can be said about mean absolute error, where you take the absolute difference between predicted and ground truth values. However, the shortcoming of those metrics are the different behaviors or different conclusions that you come looking at those numbers when average number of your ground truth labels equals to 100 or equals to 1. So in case R must equal to 1, in the first case is very good result, but while in the case when all your numbers labels are around 1, it could be a rather poor result. To address these shortcomings, one can estimate errors of the relative numbers. So you take the difference between predicted and real value, real number, real label, and divide it by ground truth label. So it's easy to understand, and it is not that sensitive to scale of the label. Another quality metric that you can introduce are relative squared error. So in that case, you divide the difference between the ground truth and predictions by difference between the ground truth and mean value of your label. So it shows you how far away from the very naive approximation of labels your model is. Or similar intuition when you use absolute difference between labels and predicted values or mean values. By the way, this difference is called L1 norm, and difference that is used in relative squared error is called L2 difference. So this RSE shows how the prediction error differs from the standard deviation of the real values, and it is much more robust to the scale of labels in ground truth. Other quality metric is root mean squared logarithmic error, which is much more robust for cases when your matrix changes in the several orders of magnitude. So here is a quick demonstration how different metrics perform for several cases. So you see that MAPE is quite different here, and it mainly because the scale of ground truth labels and predicted labels are very close to 0. So it's basically sitting around 0. If you look at mean absolute error and relative absolute error, those are a little more robust when you add an outlier. So you see that other two metric RMSE and RSE has changed significantly when we added those outliers. And it is a known property of L2 norm because you take a squared distance, and which could be rather significant for this case. Okay, now let's switch to metrics for classification tasks. So the problem formulation is illustrated on this picture. You have two features, and you have a binary class label. So you paint every pixel in this feature space either in blue or in orange or pink or whatever it is. And you have to find such a division boundary that would separate blue and red points as clearly as possible. So, intuitive way to measure such classification quality would be introduction of so-called confusion matrix. So you compute 4 numbers which are true positive, correctly predicted positive, false positive, that positives predicted by our model, but those are negative by ground truth, or true negative, that are correctly predicted negative, or false negative, that are predicted as negative but positive by ground truth. So you can plot those 4 numbers into a single table, like you see on this picture. So you have actual values, ground truth values, positive, negative, and predicted values that are also positive and negative. So in this matrix 2 by 2, you put those 4 numbers into. And what are those true negative and true positive numbers correspond to on this picture? So those are false negative. So those are falsely classified as negative, but those are positive. And this blue set is a positive set of positive samples. Those are false positive, and red on the red background is true negative, and blue on a blue background is true positive. You can deduce number of positive, total number of positive, total number of negative classes, all positive predictions, all negative predictions. And then to switch to relative numbers, you can estimate such metrics as accuracy, so which is ratio of true positive and true negative divided by true positive, false negative. Actually, it is a total number of elements in our data sample. But we are interested how many correct guesses we made, and that's why we're interested only in true positive and true negative in the in this ratio. Error rate is effectively 1 minus accuracy. And those metrics measure classification quality for both classes. You can focus on only one, for example, if it is more important for your problem. And on top of those metrics that we saw before, we can introduce so-called precision, which is a relative number of truly classified elements, or recall, which is a number of truly classified positives divided by all positive samples in our data. And sometimes you're interested both in precision and in recall. And precision says basically how many errors you did among the elements predicted as positive, and recall says how many positive examples have you selected by your model out of all positive examples out there. So sometimes you're interested in both, and one of the ways is to introduce another metric that is called F1. So it is basically precision multiplied by recall and divided by precision and recall. So here is an example for classification problem here. And you may notice that it is symmetric in terms of number of classes, and it's both correctly and incorrectly classified. It's also symmetric. Sometimes you might predict not a binary output like red or blue, but you may predict a probability of a point to belong to a positive class, like for example logistic regression. When you have numbers equal to 0 along this white line, and which means that classifier is not very confident in the decisions it makes, and it is gradually decrease or gradually deepens towards the end of this picture, and making it more red and blue. So one of the ways how you can deal with the decision boundary, you can assign a certain threshold to this probability and say, okay, my prediction equals to 1 if the probability outperforms this threshold and 0 otherwise. And if you have this information, like intermediate information or probability information about every point, we can introduce so-called receiver operator characteristic. So it is curve that show dependency of true positive rate from false positive rate. 4 different thresholds that we apply to the probability prediction of our model. So with true positive rate, depending on this threshold, can be described by the following formula. So we sum over all positive elements, and we want to know those who have been correctly classified, or that have weight probability higher than selected threshold. So it is a function depending on this threshold. And similarly, you have this false positive rate that is number of negative points that were correctly classified as negative out of the total number of negative elements. And it is also a function of the threshold. So varying this threshold, you can plot these false positive rate points and true positive rate points, and you get a curve similar to this you have at the picture. Sometimes in physics, people draw this picture a little bit differently. So they want to interpret signal efficiency and background rejection. So it's how many signal has been selected by the classifier given the threshold, or how much background we have removed from our sample by the classifier given the threshold. And it's basically the same picture, but rotated a little bit, because signal efficiency equals to true positive rate, and background reduction equals to 1 minus false positive rate. And those ROC curves are like extremely popular way to measure classification model quality. And you can compare two different models by looking at the area under ROC curve. So you just compute how much area does it cover, and naturally the perfect classifier goes from 0 to 1, and then from 1 to 1, 1. Unfortunately or fortunately, it's not very easy to get such classifiers easily for every problem, and in real life you get something in between, and you assess the quality by computing this area under ROC curve. Similarly, you can plot a so-called precision recall curve. So you plot recall as a x coordinate and precision as y coordinates, and you plot taking into account the probability threshold applied to the output of our model. So let's train a model with equal number of objects in each class, and then we fix the model and change the class balance in the test sample. And you see that we have much smaller number of red dots, and if you reduce it by a factor of 10, you see that the accuracy precision recall has been reduced also like at 10%. And for metric that is called recall or ROC AUC, those do not change with the class balance changing. However, for accuracy it is not true, because in general you might be interested in absolute number of well, in accuracy you divide absolute number of correctly classified by total number, but if your positive class is much smaller than negative class, then you're interested only in small fraction of the correctly made decisions, or on some restricted volume in the phase space. So this brings almost to conclusion of this small episode. Here we have a small question that you can use to assess your own understanding of the world, or which you can use to assess your own understanding of the topic. And so try to mention which quality for regression is more robust to outliers. And it brings us to the final summary. So we covered different metrics for regression and for classification, taking into account the mostly popular used ROC curve and ROC AUC metric. Thank you very much, and see you in the second episode in a second.